All right, chemists. So we are starting chapter 15. We are getting like this. There are only 21 chapters, and we're already on chapter 15. So we are really flying through stuff. Luckily, now we can start to relax. Not relax. I shouldn't say that word. I'm tempted to like stop and start over again. We can take more time with the individual units, so we can delve in more deeply to them and get better understanding. Chapters 14, 15, and 16 tend to be the ones that students find most challenging. Okay, so chemical equilibrium is chapter 15. This is going to be the first chapter on our first test in term 3. Okay, so term 2 is almost done. This will be the first chapter. Chapters 15 and 16 will be our first test in term 3. So this is actually an entire AP big idea, is that bonds or attractions can be formed and broken, and they're in dynamic competition, sensitive to the conditions and changes, essentially. I'm rewording it to make it a little bit more understandable. All right, so things you should know. 15.1. Color. I'm going to call razzmatazz red, because they both start with R. All right. So just for those of you at home, Griffin has a list of colors that he's going to go through one at a time. So any reaction can theoretically go in the reverse direction as long as the products are trapped in a closed system. So what that's saying is, if I'm reacting A and B, and I'm making AB, well, at the same, as that's happening, A and B can react to make A plus B. So closed system means exactly what it sounds like. It's not open to the environment. So if I had A and B, like these could react. A and B can react, but then and make AB, but then A and B can react and make A and B. So it's going back and forth. Which is, I swear I didn't look, is the title of your next slide, back and forth. So, in theory, every chemical reaction that happens is reversible, right? But, practically speaking, it's not going to appear reversible. So what would be an example of a reaction that does not appear reversible? When you burn methane, do you have another one? I thought I saw a hand up over there on the side. All right. Burning methane would be one that you would not think would be reversible. Any others? Acid-base reactions you would not think would be reversible necessarily. One that we did, precipitation reactions, might be ones that you don't think to be reversible. In most of your chemistry life from here on, from up till now, you've looked at equations like this and only had an arrow going one way, right? So you've had an equation like A plus B makes AB, and that's just how you thought things happened. And in some cases that appears to be true. So if the products are much more favorable than the reactants, so this would be something like combustion, acid-base, a lot of acid-base reactions, etc. Ones that appear to go all the way. You're not left. We talk about limiting reactant. Chapter 12 and 13, there was a lot of limiting reactant stuff, right? It goes until one of the reactants runs out. That's the way we've looked at chemical reactions till now. And in some cases, in fact, in many cases, that's an awesome hypothesis or an awesome simplification, because it goes 99.9999 through. Or it'll not appear reversible if the products escape. So when you guys were just doing that kinetics experiment, if you were doing the mass, so just the last group that just went, you measured the change in mass, right? The CO2 was allowed to escape. But for those of you who did pressure, you were trapping the CO2. So really what was happening is your calcium carbonate was dissociating and making carbon dioxide and water, but also some of that carbon dioxide was reacting with the water and pushing the reaction the other way. It didn't appear that way because the products were much more favorable, but the backward reaction was also happening. So for reversible reactions, we use a double arrow to connect reactants and products. So this is what's on your sheet right here. This should look a little familiar from the last test. Is that we have acetic acid, right? Stuck together because it's a weak acid. So we have acetic acid reacting with water, and it makes the hydronium ion. This is what makes something acidic. Plus the acetate ion. So that's happening. That's going back and forth. These two things are reacting to make my products. Your products are reacting to make your reactants.
Back and forth rates. So we learned that from kinetics, the rate of the forward reaction will depend on the concentration of the reactants. So like R equals K times concentration of reactants, and this is, to whatever order the reaction is. But now we throw in this idea of the reverse reaction. The rate of the reverse reaction, and I'm going to put Kf for moving forward, Kr, because it's not going to be the same K. The rate of the backwards reaction, or reverse reaction, is related to the concentration of the products to whatever order it may be. So the question was, is this and this the same thing? Oh, so we're going to look, let's just take this A plus B makes AB. So I would have, assuming I have first order for A and B, I'd have my forward rate equals K A B. My backward rate equals R equals, sorry, I put the KF, K reverse A B. Because I think what you're getting at is that the products of one thing are the reactants of the other, right? But now let's look at it with this side being the reactants and this side being the products. Okay. Now, as the reaction proceeds forward, the concentration of, we'll just say A and B in this case, my reactants. What happens to the concentration of my reactants as I start the reaction going? It goes down. I'm using it up to make products. So what does that mean about the rate? The rate goes down too. So as I'm having this reaction happen, I'm making AB. So what happens to the concentration of AB? Goes up. And what happens to the rate of the reverse reaction? It increases as well. And at some point, you will come to a place where the forward rate equals the reverse rate. So the forward rate will slow down, the reverse rate will speed up, and eventually they'll meet somewhere. So in a nutshell, chemical equilibrium occurs when the forward and reverse rates of reaction are equal. Okay, we ready to move on? Still need a little more time? Good. Speak now or forever hold your peace. Speak up. All right. So, here's some big ideas. 15.2. At first, the forward reaction rate is much higher than the reverse. This makes sense, right? Because I have a lot of reactants at the beginning, so my rate is going to be higher. I don't have a lot of products. As the reaction proceeds and more products are made, the reverse will start to rise and the forward will start to fall. When they are equal, the concentrations remain constant and the reaction is at equilibrium. These are big ideas, especially this one right here. Now, here's the big misconception. If I say my concentrations are equal, a lot of people or a lot of students typically say, okay, then the reaction stopped. Nothing is happening. That's not true. Equilibrium is dynamic. That means the forward and reverse reactions are still occurring, but they are at equal rates, so there is no net change in concentrations. And I have a little demo or not demo, but visual I'm going to show you guys after you copy this down. So don't think of equilibrium as static. That those substances just stay the way they are. They're constantly going back and forth. Okay, so now we're going to look at a hypothetical reaction. And we go here. Okay, so here I have a closed container. My reaction is A plus BC makes AB plus C. And here is, oh, this should look kind of familiar, right? Sorry for those of you listening at home. You have no idea what looks really familiar. This, I don't know if this is going to show up. Oh, the arrow will show up. This should look familiar, right? So we're going to be looking at what kind of reaction? Is it endothermic or exothermic? Endothermic. Our reactants are at a lower potential energy than our product. So I'm going to pump in, let's say, 25 A's and 25 BC's. And while I do that, I'm going to have a bar graph that shows me how many A's and how many BC's I have, okay? So we have A and BC, not a lot of reactions happening, right, at this point? Well, why do you guys think not a lot of reaction is happening at this point? Yeah, well, it could be a concentration thing. It could also, we had a little bit. There's not a huge amount of total average energy. So not many of those particles are able to get over the activation energy hump. So let's see what happens when I increase my temperature. See the nice little flame. Okay, so now I'm starting to get more product being made. But what do you guys notice happening to the product? Is it staying the same? No, it's varying. It's going up and down a little bit. So at any given time, it's hard to watch an individual one because they're moving so quickly. But if you can keep your eye on, let's just say, so they're moving too fast. But you can see that they're going back and forth between their reactant state and their product state. Eventually, I'm going to reach a point of equilibrium. It doesn't mean I have equal concentrations of product and reactant. That's not what equilibrium means. That's another thing that is a common misconception, is that equilibrium means I have equal amounts of products and reactants. That's not true. It just means, in general, my forward and reverse reaction rate is not changing. So I can also increase the temperature again and shift the equilibrium. So let's really get these guys moving. All right. So now things are happening a lot more quickly. Let's see. But see how I'm staying in general? Well, I was staying in general. I'm staying at about the same concentrations once I hit equilibrium. Let's slow it down some. If everything's over the activation. Oh, not up. All right. Let's let it just calm back down for a minute. So at this point, my concentration of A and my concentration of B, they're staying about the same. My concentration of AB, my concentration of C, they're staying about the same. So I'm reaching this equilibrium point, right, where the forward and reverse reactions are the same. It doesn't mean that it stopped happening. It just means that my concentrations are staying the same. Now, we're looking at a small number of particles here, right? We're looking at a total of 30, 40, 50 particles. When we think about chemical reactions, we're thinking about moles of this, right? So we see a lot of like movement here, but imagine if you had a mole of this, all of those things would be averaged out, right? All of those little fluctuations would get averaged out over the entire mole of things reacting. So you'd see a little bit more constant when you have more of them. Yes? So the question was, in equilibrium, the concentrations don't have to be the same. So I can, it's not even true. That is very true. I could actually, right, so I can actually make this different as well. So I can add in a ton more BC, right? My product's concentration, even they don't have to be the same, right? So none of these concentrations have to be the same. They just have to reach a point where the concentrations aren't changing anymore. That's when you hit equilibrium. Slightly, like you see here, slightly. Yes, if you looked at this over like a mole's worth of particles, you wouldn't even see nearly this much movement because it would all get averaged out. Oh, the question was, will the reaction reach perfect equilibrium when the total average energy goes above this? No, because you still have one side being more favorable energetically than the other. I don't know if you could ever get perfect, like 50-50 balance between. Yeah, it'll happen. It's different for each different reaction that you have. All right. So did this make sense? Was this like a good visual? I know these are moving a little too fast for you to see. I mean, I could show you like the individual single collision, but this doesn't. I mean, that's just kind of neat to watch. It's it's not really helpful to understand equilibrium, but it's kind of neat. And now it's ruined. All right. Nope. It did hit it, but it didn't hit with enough energy to overcome the activation energy to make the reaction happen. Nope. It's done. Sorry. Okay. So that shows you guys equilibrium's dynamic. And this is going to be awesome because I love it when I write over things and not realize that there's text underneath what I've written. So just because the concentrations are not changing doesn't mean the reaction has stopped. In post-production, I'll move that writing out of the way. Okay. So rates and equilibrium. So imagine we have the following elementary step. This is our reaction. I have A moles of A plus B moles of B makes C moles of C plus D moles of D. So at your tables, I want you to come up with the rate law for the forward rate and the rate law for the reverse rate. So this is something to do. You guys can talk to each other if you want. You don't have to be social. I just like talking to people. But are you guys jumping ahead? Yeah. We're deriving here. You don't want to jump ahead. But you wrote the answer in the next thing. All right. I won't tell you the right answer. Okay, guys, let's come back. What is the forward rate equal to? Somebody? Anybody? Lior? So if it's elementary, that A, I should have been more specific. These are the coefficients. So it is the concentration of A to the A power times the concentration of B to the B power. And what is the reverse rate? Somebody else? It's Sydney. Yes. Yes. So for any elementary, the question was, I thought the coefficients weren't the exponents. For elementary steps and rate limiting steps, the coefficients are the exponents. So if I tell you I have an elementary reaction, like in this case, you can say that the coefficient is the superscript. That's what I mean. All right. So at equilibrium, what is the relationship between these two rates? Well, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. So from that, we can say that K forward, A to the A times B to the B equals K reverse, C to the C over D to the D. Now, these K's are constant values, right? So if I get these on if I get both K's on one side of the equation, that means I'll have a constant, right? So if I divide this side by, if I divide both sides by KR, all right, so I have KF over KR equals, and then I'll do the other part in my head. What we call this expression is KEQ. We don't call it KF over KR. We call it KEQ. The equilibrium constant for this reaction at this temperature is described by this. And it is a constant value. It's constant for a given reaction at a given temperature. Yeah, which is written right underneath. Yes. I forget. Is it big K or little K? It's big K. Big K. I mean, if you put little K on a test, I'm certainly not going to take any points off. Oh, Mr. Hamill said he'll take points off if you put little K on a test instead of big K. I'm grading your tests, but different.
This is why I put the little hook on small K. No, big K.
Different chemistry teachers have different things that they find extremely important. I like phase diagrams. Yes. Mm-hmm. The question was, is it only for the K of equilibrium? Yeah. So you still have the small Ks from the reaction rates, right? All right. So, summary. For a given reaction at a given temperature, the ratio of products to reactants will reach a fixed value called the equilibrium constant, K, described by this equation. Okay. So now, a reaction might not actually be at equilibrium yet. Things will move toward equilibrium, but they don't necessarily have to be at equilibrium when we're looking at them. So we can generalize beyond elementary reactions. So for any reaction, look at this one. So I have my first reactant plus my second plus my third, all the way to the end. Makes product 1, product 2. This should be N, product N, right? The reaction quotient, Q, is defined by this. So it's that same idea of products over reactants. And this Q, this is at any given point in the reaction. We're actually going to use Q to determine what direction the reaction will move. And we'll use Q to determine if we're at equilibrium or not. No. So the question was, is this the same Q as in Q equals MC delta T? This has nothing to do with energy. Nope. It's just Q. And Q is not a constant value. Q will change depending on where we are in the reaction. Right? So at any given point, the Q will be different. And once we solve for that Q, we can figure out which direction the reaction is going to go. We'll get to that in a couple slides. All right. So the equilibrium expression. Here we go. For any reaction, when it reaches equilibrium at a given temperature, the reaction quotient reaches a constant value. So we've already talked about this a little bit. We call that KEQ. So the equilibrium expression is the equation that sets KEQ equal to the reaction quotient. So when Q becomes equal to KEQ, we are at equilibrium. So it looks like that. So you'll notice that this is the same idea as the slide before. Except the difference here, this is a constant. I can take my Q at any point in the reaction, but my reaction will go until it moves towards this value, this KEQ value. Yes? So if it's not at equilibrium, we use the same equation, but we're given, in this case, we're just given a value for Q that sort of tells us where along the reaction we are. Right. And then we can compare that Q that we get to what we know to be the equilibrium value, and that'll tell us if we're at equilibrium or not. And if we're not at equilibrium, it will tell us which way the reaction will go to reach equilibrium. Okay. So notes about Q and K. So equilibrium expressions in general, they refer to concentrations of dissolved species, and I'm going to put generally H2O as the solvent, or partial pressures of gases. The both good and bad thing about gases is that we can use partial pressures or concentration, which is it gives us more variations, but you know, it's nice to have options. So except if we use the designation Kc and Kp to distinguish between concentration and pressure. I'll set a few of these up in a minute. But Kc is when we're using concentrations. Kp is when we're using pressure. So the equations look the same, except in Kc, you're using the concentrations. In Kp, you would set it up like you would set up the Keq, except you're using pressure. If no subscript is listed, you just have K, use the partial pressure. Now, here's a big one that always shows up on tests, on AP exams. The concentrations of solid and liquid reactants and products essentially remain constant, so you don't put them in the equilibrium expression. So anytime you have a solid or a liquid, that does not go into your KEQ equation. Right? Because if you have a solid, again, visuals for people at home. All right, if you have, I think I'll just unplug it. If I have a solid and it's reacting with a liquid, really, the concentration of the solid isn't changing. It's being used, but the concentration of it, the amount is going down, but the concentration of it isn't really changing because it's a solid. It's like 100% concentrated, if you want to think about it that way. So since we can't use concentration values for solids or liquids, we leave them out. We assume that they're not involved in the equilibrium. Now, obviously, if one of your solids ran out completely, well, that's a different story. But when we set up these expressions, you leave solids and liquids out of the picture totally. Any questions? All right. Okay. So now, what is the relationship between Kc and Kp? You know what? We have 15 minutes left. So I was going to derive this myself, but I will tell you, I'll give you this reaction. So, all right. Thank you, chemists, for pointing out that it was coming up despite me not realizing. Okay. Oh, I need to go back to arrow, go forward, go forward, go forward. There we go. Okay, we have this reaction happening in the gas phase. So, I know that technology, yay. I can't use the remote. All right. So, my Kp for this would be my partial pressure of A to the A power Wait, whoops, nope. Erase. What did I do wrong? It's products of reactants. Partial pressure of C to the C power times partial pressure of D to the D power over partial pressure of A to the A power times partial pressure of B to the B power. My Kc would be concentration of C to the C times concentration of D to the D over concentration of A to the A, concentration of B to the B. Use your knowledge of gas laws to derive the relationship between Kp and Kc. Basically, how can you relate pressure with concentration? I'll give you guys, 5-7 minutes at your table. We have time. I only have one more slide I want to go through after this. So think it through. Try to figure it out. How can you relate Kp and Kc? Thank you, sir. What do you think, guys? Do you want us to do it together, or do you want to work on it on your own? All right. So here's what I'm going to do, guys. This is I know it's the end of the day on Friday. So I'm going to use Kp if I can get the marker to come up. All right. So for Kp, I'm going to set that equal to, I'm going to switch out. Instead of partial pressure of C, I'm going to put concentration of C times RT to the C power. I can do that. I just substituted it in nRT over V. And so I do the same thing for concentration of D times RT to the D power over concentration of A times RT to the A power. This should be little d. And then concentration of B times RT to the B power. Now, I'm going to take a little leap. All I did, guys, was plug in. I just plugged this in here. And I knew N over V was equal to concentration. So I'm going to change this now to look like this. I did not mean for this exponent. I only ever write D's at the beginning of my first name, so they're always capital. I'll use that as my excuse, Jake. And these, and my last name also begins with, I have no excuse for the A. I mean, you could do, yes, you're right, RT would be in parentheses, yeah. Because it's not T to the A plus B, it's RT to the A plus B. Yes? It helps us figure out how Kp, which is the equilibrium expression for pressure, is equal, or relates to Kc, which is the equilibrium expression for concentration. So if you're given a problem where you have gases, and you're given the Kp, I could ask you to find what is the Kc for this reaction. So the question is, would we be given the Kp value? Yes, you'd be given the Kp value, and then I would ask you what the Kc value was. So what this turns out to be, this is this, right? It's the same thing. So it equals Kc times RT. Now, I'm going to put it as delta N, which delta N is the difference in the number of moles between equals moles, total moles of product minus total moles of reactant. And I could do this all out by saying C plus D minus A minus B. If you did the math right for this step, you just get RT to the delta N. But where your delta N is your moles of product minus moles of reactant. In this case, it would be C plus D minus A minus B. But for most equations, you're not going to have A's and B's. You're going to have 1s and 2s and 3s and 7s and 18. Yeah. Yes, that only works. The question is, does that only work if you use elementary stuff? So for these equilibrium expressions, that's what you're going to be. That's what you're going to have. Right? It's all set up to work that way. Okay. So that was a lot of math that really we had extra time. I could have just told you that Kp was equal to Kc RT delta N. But, you know, a little bit of mental math for you on a Friday. All right, last slide of the week. Write equilibrium expressions for the following reactions. So I want you guys to take 2 minutes at your table. Write equilibrium expressions for each of these reactions. That's the only thing I would take issue with. I don't like legends like that. But because that's a little too much information there. It's taking away from the beauty of the graph. But I mean, that's a very solid graph.
A lot of great.
So no, aqueous is solution, in solution. So those are the ones you use.
So you can use aqueous or use like this or something.
Right. So the question was, how are we supposed to find the K of equilibrium? It's a given number. It's a constant number that you'll either have to solve for or you will be told. Oh no, there's no way. Just want the expression. There's no way you could be given. You could get a number from this.
Can I drink CH3O? Can I drink H3O? Will it taste like
It would taste bitter. H3O plus. Think about lemon juice. H3O plus. It's acidic. Sour. That's what I meant. Sour, not bitter. Sour. Whatever lemons are, sour. Okay, chemists. So here are your answers. I gave you Kp and Kc for this. You could have done it partial pressures. They're both gases for this top one. So here is your Kp. Here's your Kc. For this second one, we don't have gases. So we just have, wow. We have no gases, but we do have a liquid, which is not involved in our equilibrium expression. So that is not written in our Kc. As you can see, there's no evidence of H2O as one of the products. And in the last case, the dissolution of lead chloride. Well, lead chloride is a solid, so that's not involved. So our Kc would just equal that. We will practice these on Monday. You owe me a lot of stuff on Monday. I hope you have a wonderful weekend that is filled with a small amount of free time, but sufficient amount of time to get the work done that you owe me. Yes. Wait, hold on one second. And guys, I'm here now. Like if you have questions, I'll be here for an hour or two.